Hello and welcome back to part 2 of Introduction to Hydraulics. My name is Andy Dibbling, and again I will be your facilitator today. First slide we're looking at here is a small hydraulic motor. This motor is driving this shaft, which will help position a wind turbine rotor. So this is a positional motor that can go both directions and has a very precise control, which is something that hydraulics can offer. You can get speed, you can get power, you can get excellent placement. All of these are properties that can be brought out in a hydraulic system depending on how you manipulate the fundamentals. That's what we're going to be talking about today, some of the fundamental science behind how hydraulics work. Quite simple. We've been using them forever. The Archimedes screw, for instance, is a hydraulic device. We have been using wind power forever and Archimedes screws and bucket wheels to move water around, which is another hydraulic system. A pump. Fluid power is something humans have been using since we've been around. Okay. So in any hydraulic system and any fluid system, there's a relationship between force, pressure, and area. Theoretically, in a hydraulic system, force in is equal to force out, plus losses. Now, those losses can be minimized if the design of the system is such that it reduces those losses from friction, from heat, from vibration, all of those waste energies that you can get out of any system, not just a hydraulic system, but some of them are uniquely parasitic to hydraulic systems. In this example, distance and speed were exchanged for force. This would be similar to a hydraulic jack that you would use to jack your car up. If you have a regular everyday bottle jack, you know that you have to pump on the handle 10, 15 times in order to get the output piston ram to even move a little bit. That's the same kind of a system that you have here. And that's basically a system at rest. The fluid is being worked on by either the pump or a bypass valve, which returns the fluid back to the chamber to repump it when you want to reset the jack. This uses more Pascal's laws than it does Bernoulli's, but still a hydraulic system it is. In this case, we will use a long distance. We may be jacking this thing 10, 15, 20 times to get a little bit of fluid to move into this larger diameter cylinder. The larger the area, the more pressure is applied for the same amount of force. So this is a wonderful little equation, FAP. I should have it as a tattoo, actually. That along with E, I, and R from my electrical work. Force, area, and pressure, we're always changing these criteria around to get what we want. All right, so this is your typical bottle jack. You'll also see this used in the car to apply the brakes. You push your foot down on the brake, it travels 3 or 4 inches. It's then put through a large diameter master cylinder, which concentrates the force on a small output, giving you a lot of pressure. And that pressure is then exerted on a large area on the calipers. However, the calipers move a millimeter at most. So the same kind of system. You're changing distance for force. Right. Okay. Moving right along. Gases and liquids are both fluids. So are plasmas. Plasma is a little too hot to deal with in our realm of things, but gases and liquids you should be fairly familiar with. We've all blown up a balloon. We've all blown or sucked air out of a plastic bottle. So you understand the basics of atmospheric pressure. A gas is molecules that are not tightly bonded to each other. They could be bonded with another molecule of their type, as in O2, or in carbon dioxide, bonded to a carbon atom. But generally, they are autonomous little molecules that float around bumping into each other. They are at a fairly high energy state. Liquids are more tightly bound. They still have freedom to move and will take the shape of their containers. However, they don't have as much freedom and can't be as compressed. The space between them is less than in a gas. We'll use these properties of gases and liquids in hydraulics and pneumatic systems, as well as in refrigeration, steam engines, all kinds of applications. We've been using these type of mechanical forces forever. In a hydraulic system, which we're going to talk about first, it's the liquid that we're concerned about. The liquid is virtually incompressible. What that means is you can compress it a little bit, maybe 0.5%, but that's about it. It's a little less compressible, or a little more compressible than a solid, which isn't much at all, right? Okay, so by the ability of Pascal's law, by putting a force on the top of this liquid, that force will be spread out equally at right angles to every side of the container equally, no matter where you are. And this is a wonderful property that we use a lot to get stuff done. Okay. So Pascal's law, as mentioned, applies to a confined fluid. The pressure is transmitted equally throughout that fluid. And Pascal's law, is something that we use, like I said, on things like bottle jacks or systems that don't have a pump. It's a sealed amount of fluid, a finite amount of fluid within a container, and then we just move that fluid within that container around, and as a result, we get the energy that we want where we want. Okay, this is a little different. When a restriction is placed in a fluid stream, such as in a pipe, an increase in pressure and a reduction of flow is achieved. So this is known as Bernoulli's principle. Bernoulli had found that when you increase the velocity of a fluid, you reduce its pressure. And when you reduce the velocity of the fluid, you increase its pressure. So of course, just like trying to get onto a crowded subway car in Shanghai at rush hour, it's very difficult to get onto the subway car because of the openings of the door, and there's a pressure behind that. And if you've been in the platform, which I know you have, in any major city, you know that pressure can be significant, and you may, just like the molecules of fluid, have very little choice but to go with the flow, as it were. So a mistaken belief is that a pump is what creates the pressure. A pump does not. A pump creates flow. Flow, only when it meets restriction, builds pressure. And that's an important concept to remember, because we use that concept all the time to transmit hydraulic power from where it's generated to where it's used. For instance, here we have a schematic representation of a front-end loader. Now, of course, total pressure is equal to pressure losses plus pressure required to overcome the load. And this is a very important concept. In a hydraulic system, as well as in an electrical system as well, but in a hydraulic system, only as much pressure will be provided as is required to overcome the load. If the load pushes back harder, the system pushes back harder against it. But it doesn't work any harder than it has to. Of course, there is no system that doesn't have losses, and the losses in a hydraulic system are predominantly heat. Some in vibration, some in noise, but mostly heat. And heat is very destructive to hydraulic systems due to the viscosity of the fluid. The fluid's viscosity, or its thickness, is temperature dependent. Now, a lot of the properties of hydraulic fluids are designed that they will have the correct viscosity or thickness over a large temperature range. However, there are limitations to that. So it's very important to remember that heat is to be avoided. Now, you can create excess heat in a hydraulic system accidentally. Pressure relief valves are a perfect example. If I set a pressure relief valve, it's setting too close to the working pressure of that unit, I will get a lot of pressure relief valve cycling, and all of that is wasted energy. So I want to, your pressure relief valve is a fuse, just like a fuse on an electrical system. I don't want it to operate as a switch. I want it there in case of emergencies to prevent some kind of catastrophic failure of either a conductor or an actuator or a cylinder or a motor, right? I don't want the pipe to burst. I want it to dump it to tank. But it's not supposed to be part of day-to-day, moment-to-moment operations. If it is, then the system is designed incorrectly. Okay, so that's something to keep in mind. Okay, so this is an example of Bernoulli's principle at work. I mean, force area pressure. And here we're using old, well, I guess American units or British units, basically the only people in the world that use these. So if you can just suffer through them. You could imagine this being 10 kilograms of force and at 9.81 meters per second, which is the acceleration of gravity, you get 98 newtons. Regardless, 10 pounds applied over 1 square inch would equal to 10 pounds per square inch. Or, if I was dealing with, I like to deal with atmospheres or bar. BAR as a unit. You'll probably hear me talking about bar quite a lot. The reason for that is bar is a great measurement when I'm talking about hydraulic systems, because generally hydraulic systems are many, many times above atmospheric pressure. 1 bar or 1 barometric pressure is 100 kPa. A standard day, which is defined as sea level, 15 degrees centigrade, with an air density of 1.15 kilograms per meter squared, I may have that part wrong, is defined as 101.325 kPa, or 101.325 kilopascals. So I like bar because bar is 100 kPa, or 1 atmosphere. So if I'm looking at a hydraulic cylinder or an accumulator that I'm going to change out on a wind turbine system or other large hydraulic system, and I see that the gauge says 200 bar, I know that the amount of force, the amount of pressure within that enclosed cylinder is 200 times the atmospheric pressure. If I release that dragon out of that accumulator, I will immediately be hit with the atmosphere of Jupiter. I'm not designed to survive on Jupiter in its atmosphere. Hereto, that would be the end of me. So bar gives me respect. I know that anything over 1 is painful, right? Anything over 5 is most likely fatal. Right? So those are things to keep in mind. Hydraulic systems can be extremely dangerous because of the high pressures and the toxicity of the fluids. So you always want to take into account safety at all points. So that means I don't work on a hydraulic system without gloves on or without safety glasses on, simply because you only have 2 eyes and you only have 2 hands, and they're too easy to lose. If you want to have a long career, it's very important that you take care of your best assets, which is your mind and your body. Okay, so here's an example where if I take 10 pounds of force and I put it to a 2 square inch area, I end up with a reduced pressure of 5 psi, or half of what was there in the last example. It's the same amount of force, but the area is bigger, so the pressure will drop. Again, the restriction is what makes the pressure, right? Restrictions also govern flow, or the speed of which things travel. So it's important to understand that if I'm adding a restriction to the pipe, while I might be adding pressure and force to the system, I am going to be reducing speed. It can't act as fast because it has to build that pressure, right? Okay, so here we have an example. We have a 1-to-1 ratio here, 10 pounds in, 10 pounds out. 1-to-1, there is no change in area. Now, in this case, we have a change in area. We have a change from 1 to 5. So, of course, I'm going to find the area in square units, square millimeters, square inches, and I'm going to find that this is now going from basically 1 bar over here, right, to 10 bar over here. By changing the area here, I have increased the amount of force by building the pressure. But again, my distance traveled will be less. So you don't get something for nothing. It would be nice if you did, but you don't. So you always have to give in order to take. Okay. So here's an example of a very simplified hydraulic system that is designed to run a linear actuator. And these will be basic components that you will have in every single hydraulic system. Most of them that we deal with are going to have pumps and reservoirs. All of the reasons for each of the components will be explained, and they all have to do with system efficiency and with output, and depending on what you want the system to do. So we have a reservoir. Reservoir holds the fluid. It also cools the fluid, allowing the fluid to dissipate heat to the atmosphere to maintain its viscosity. Also in the reservoir, you're going to have some settling of the fluid, which means that any kind of contaminants picked up as the high pressure fluid wandered around its system, either little bits of the rubber that have come off the seals or the inside of any of the conductors or hoses, or little pieces of metal that it's picked up as it's gone over control valves, microscopic pieces will get a chance to settle out or be caught up in the inlet strainer, right? A good place to look at the health of your fluid is the reservoir. It will tell you if you have water contamination, because water will settle out to the bottom because the hydraulic oil is lighter, has a lower specific gravity than the water. So as a result, the water will sink. Also, too, a lot of the precipitates will fall eventually. There's generally a baffle or two in a reservoir to prevent like gurgle loading, where the fluid will slosh, and that could end up the pump sucking air in, which is a really bad thing. You don't want your pumps to suck in any air. You want to avoid that at all costs. And a lot of the design of pumps and the inlets are designed to minimize the possibility of sucking up air. Okay. Next thing, we have a pump. Pump provides the motion to the fluid. It provides the flow. Now, the flow control valve is what is going to determine how fast the flow gets to the actuator. Now, remember that it's a saw-off between speed and pressure. So I could have the full pump velocity of the fluid going to the cylinder, and it may go very fast, but it may not have the ability to move any load whatsoever because it doesn't have a chance to build pressure because there is no restriction to that fluid. Okay, so the flow control valve here will meter the fluid down. The relief valve is designed, as I mentioned before, to provide a pressure relief if design pressures are going to be exceeded or pressures such that could damage the system. Sometimes you'll get them go off as well if you've had a big load shift. 3 or 4 things shut on or shut off at the same time. That can take a pump that's been running very hard and all of a sudden give it a large restriction, which will drive the pressure up. That may temporarily pop your pressure relief valve. That's kind of what it's there for. It's not there for, as I mentioned before, everyday running conditions. There are other ways to regulate pressure than just using your relief valve to do that with. It's more like a fuse or a circuit breaker. Okay, from the flow, you have this control valve, and this is a rotary control valve. So we're looking at the darker fluid being the high pressure fluid, and it will come into the front of this cylinder and will retract it. Now, when we flip the valve around the other way, the pump is still pumping the fluid in the same direction. The relief valve is still set at the same pressure. The control valve is still running the fluid through the same direction until it gets to the control valve where it is changed 180 degrees and now comes in from the back side of this cylinder. Here's the thing. This system is designed so that it has more force going outwards than retracting, similar to a trash compactor on a garbage truck or something along those lines. What I'm designing this system to do is basically act with a lot of force in one direction. It has the ability to retract itself, and the force would be significant, although nowhere near the force as it's being extended. The amount of force, of course, differential is going to be determined by the size of this rod. The heftier this rod, the more area it takes up as a restriction against the fluid, the less force will be generated. Okay? All right. And that's basically the long and the short of it on how hydraulic systems work. Speed for force, and pumps make flow, restrictions make pressure. That's your big takeaways from this one. Here's a little slide on the viscosity of oil, and this is at minus 35 degrees C, and there's a lot of places where it gets to minus 35 degrees C. I've worked in several different industries where this is not a temperature you don't see a lot for 2 or 3 months of the year. As a result of that, we've had systems where we just leave them running 24 hours a day, because if you shut them off, they quite literally would, especially when you get heavier oils, heavier gear oils, lubricant oils, and large machinery, they will literally turn into this basically syrupy goo, and you won't be able to start them again, because it's like the crankshaft of the motor or the compressor is sitting in tar. It's not moving anywhere, and if you try to start it, you'll just break it. So a lot of hydraulic systems will have cooling devices and heaters to keep that oil in the right viscosity to make sure that it is able to provide power in the most efficient way possible. Okay, so this is a hydraulic gear pump. This is a pretty standard type of pump. Gear pumps are used quite a lot. They're simple, they're cheap, they're robust. You can service them. They're a bonny and a beauty to behold, that's for sure. They work very simply on vacuum coming into the inlet on the bottom of the pump here. Because the pressure on the inlet side is lower than the outlet side, obviously, and the inlet side pressure is actually lower than the vented pressure of the reservoir. Most of these gear pumps are used in systems that do have a vent on the reservoir. So the reservoir for the hydraulic fluid, while at rest, is experiencing an atmospheric pressure. It's not until the outlet of the pump and it gets in motion and hits that first restriction that any pressure is built. Okay, so as the fluid comes into the intake, it will go around the outside, and this gear tooth pocket is where the actual oil is taken around. And as the pump housing widens again towards the outlet side, the oil is ejected. Now, it can't go back down through the middle here because there's no room for it, so it's naturally vented to the outside. All right. Now, a little bit of oil will slosh back because it's not a perfect seal, and we really wouldn't want it to be a perfect seal, because this whole thing is moving at a very rapid rate of speed and is generating a fair amount of heat all on its own, and we need that heat to be dissipated. We also need the machine to be lubricated. As a result, this hydraulic gear pump will be about 90 to 95% efficient, which means that if I'm moving 10 liters of oil, a half a liter is seeping back into the inlet for lubrication and cleaning and things like that. That's not a bad thing at all. You're still getting a 90 to 95% efficiency out of the machine. And in any industrial machine, 90 to 95%, that's pretty darn good. This is old technology. It's simple technology. It's really easy to maintain. You got two shafts, you got two sets of cog gears. You're looking for wear in the housing, you're looking for wear on the teeth, you're looking for wear in the bearings, and that's about it. And wear will tell you a lot of the health of your system. Well, if I have it, wear on the inside coming into the pump, is that wear due from age and neglect, or is that due from contamination in the fluid itself? So now this will tell you, just like a bad heart in a person, will tell you a lot about the underlying health of the machinery. And that's where, as a technician, you are really most valuable. Okay, so that brings us to the end of this presentation. Please feel free to review it at any time, and you will look into the lesson 1 package, and you'll see my contact address at Holland College. I'll send you my email address. You can Skype me. You can go over this. I'd love to hear from you. Anyway, remember there is a 12-hour time difference. So noon your time might not be the best my time. Anyway, have a wonderful day, and we'll talk to you soon later on.